Thank you very much. And yeah, I gave this talk like 2 weeks ago, and the person presenting me at the time did the exact same mistake. So maybe I should change some order here in my first slides. I start to take the hint. Okay, and thank you very much. I want to, I'm very happy to be here and to describe this talk. So describe this work. So I will talk about a paper which is joint work with Alexei Borodin, which we did last year. And it's a paper with the same title, Geometry of the Doubly Periodic Aztec Diamond Model. And the goal of this talk is to, so here I should say is like a random sampling of an Aztec diamond, and on this side we have an associated amoeba. And the goal of this talk is to describe what these two objects are, and in particular to explain how the two pictures are related to each other. So the outline, so first I will talk about the diamond model, which would be the left side of the previous slide, and then go on with the spectral curve and the amoebas, which would be the right side. And after that I will talk about the action function that from our perspective is the objects that's connected to pictures. And finally, in the end, I will tell you all the results we have, or some of the results in our paper. So that's the goal. Okay, so let me start with the diamond model. Okay, so we have had one talk and we already saw the Aztec diamond, right? But I will, stay to the ordinary, the classical diamond model of the Aztec diamond. And that is this graph on the side over here. So this is a subset of the square lattice. This is the Aztec diamond of size 4 because you have like 4 vertices here on the side. And a diamond covering of the Aztec diamond is a subset of the edges such that each vertex is connected by one dimer. So here is an example. Okay, and this is maybe the classical way of drawing the Aztec diamond, but going forward I will use the same convention as before, like rotate it by 45 degrees. That's why I have this small compass. You can see the difference. And I should also say that you can instead of thinking of it from a dimer perspective, you can also associate or think of it from a tiling perspective. You simply take the dual graph, or you simply make each dimer to a block, a domino block here, and I call them so if I have this vertical dimer with the white vertex up, it's yellow. If the white vertex is down, it's blue. Then the horizontal, if it's the white vertex to the right, it's a green, and the white vertex to the left, it's red. And from my point of view, it's just to, it's nicer to show some pictures in this tiling, using this tiling pictures. Okay, and the Aztec diamond has been considered for a long time. It's probably, it's a very classical object by now, and one of the reasons is that it's a rather simple model from the dimer perspective, or from the exact solvability perspective, and it still contains a lot of interesting phenomena in the limit. So here is random samplings using the uniform measure of the Aztec diamond, and you can see of different sizes. I think this is maybe size 10, this is size maybe 30, 100 and 300, something of that sort. And you can see this kind of nice, structure appearing as the size of the Aztec diamond increases, right? You see this some in the corners you only see one type of dimer or tile, and then you have some curve separating, going from this so-called frozen region into some disordered region, and inside that you have all types of dimers, right? And what you see here is the Arctic Circle phenomena. So in the limit as the size tends to infinity, there will be a circle separating the so-called frozen region and the liquid or rough region. Okay? So I will be interested in the same type of questions, like what happens with the random dimer covering as the size of the Aztec diamond tends to infinity. But I will be considering a different probability measure, not the uniform one. So here I will try to introduce the probability measure I'm interested in. So to do that, we introduce edge weights, and we will do this in a periodic way. So here K and L are our periodicity parameters. So these are positive integers. We introduce the edge weights, alphas, betas, and gammas. And we assign to each edge of this type, we say, okay, the edge weight is gamma ji. Here, on these types of edges, we have alpha ji. Here we assign the betas. And on these ones, we assign the weight 1. And as I said, we do this in a periodic way, meaning that if you, let's say, if we follow these types of edges, so here we have alpha 1, 1, here we have alpha 1, 2, alpha 1, 3, up to alpha 1L, and then we start over. So that's the periodicity in the horizontal direction. And we have a similar thing, but with periodicity K in the vertical direction. So here we have alpha 1, 1, here alpha 2, 1, alpha 3, 1, and so on, up until we arrive to alpha K1, and then we start over with alpha 1, and so on. And similar for the other ones. So this is a period we introduce. So this is the periodic edge weights. And yes, and the probability measure is defined. So the probability of a dimer covering is it's the product over these edge weights, where the product runs over all edges in the dimer covering, and then we have a normalizing factor here to make it a probability measure. Okay? So in the simplest possible case, when K is equal to L is equal to 1, and all the edge weights are 1, we recover the uniform measure, right? And it turns out that if you do this, then you have something similar, but still like a lot more is going on when you do this. So here I've taken some examples. So here K and L is equal to 2. Here K and L is both equal to 3 as well here. Here I think K is 1, also 2 and 2. And here maybe L is 3 and K is 2. So you see you get this kind of different behavior depending on your periodicity and your edge weights.
So in the striped regions, do you have like complete, even odd, colored in stripes? So I see green, blue, yellow, red. Yeah. Is it like completely regular?
Yes, it's completely regular. Yes, exactly. It's not always alternating between like yellow. I mean, I think here you probably have like yellow, red, red, yellow, red, red, while here you have yellow, yellow, red, yellow, yellow, red, and so on. While here you have exactly yellow, green, yellow, green. So it depends on which one, but it's frozen.
Depends on the periodicity.
Yes, it does. Yes. Okay, but so you still see these like frozen corners here, right? With only one type of dimers, but you also see what we discussed now, these other types of frozen regions, which are completely frozen, but not containing two types of dimers.
So Thomas, in your middle picture, is it really a straight line? Like there is a middle picture, yes. So is it a straight line, or is it just an artifact of simulation?
Yes, so there are artifacts of simulations here. So what you will see here, it will be strictly convex here. and there will, I mean, if you look closely, it looks like it's a frozen region connected with the smooth region connected with the frozen region, and that doesn't happen. There is a small, like a thin liquid region in between.
Can there be regions where only 3 colors are present?
No, I don't think so.
So it's either 1, 2, or 4.
Yes. I think that's correct, yes. Yes. Okay, yeah, so as I said, like we have this, like we get this, still these like Arctic curves, right? Like separating the different frozen region from each other, from the liquid region. But now we also have this third region, which is here, maybe you can see it here as well, and they are actually in all of these pictures, which is called the smooth region or gas region. And there is some Arctic curves separating this third region from the liquid region as well. Any other questions on of these pictures? So I gave a similar talk at some point in Philadelphia, and when I gave the talk, when I came to my hotel room, this was the wallpaper in my hotel room. And I saw it, and I was like, I wish they have, used some coloring here in a very nice way. Maybe they would have chosen these guys to be yellow and these guys to be green, because then this is exactly what you would see if you zoom in here locally. Okay, so these doubly periodic Aztec diamonds has been considered previously, like for the last almost 10 years now, I guess. People have tried to, understand these models. And in particular, it has been a lot of work on this 2 periodic Aztec diamond, which is like the easiest possible case where you still see a gas region kind of a thing. And then there has been more recent work on this very symmetric version of where k is equal to 2 and you have a general L, and then you have very recently by this 2 periodic, but you add some bias into your model to go away from the symmetry living over here. But in all previous cases, we have been, which has been been analyzed, k is equal to 2, and okay, I will not really tell you what this means, but the edge weights, there is some extra, extra symmetry in the edge weights, which says that they are at a so-called torsion point. I will not go into that, which also simplifies the analysis. And we are able to go away both from the k is equal to 2 case and also this torsion point case. Okay, so that's the model. Let me now continue with the spectral curve case, or the spectral curve to define. So now we forget about the Aztec diamond for a moment, and now we only consider the edge weights which we had from the beginning. So if you remember, we had this periodicity k and L, and we assigned these gammas, alphas, and betas to the edge weights. So now we take the fundamental domain, which is the smallest non-repeating part of the graph, and we embed it in the torus. So we identify these vertices together with these vertices up here, and in the same way we identify these vertices with these vertices. Okay, so this is something living on the torus now. And going from, and in this torus, you have the two closed loops this one, and we introduce these magnetically altered weights. So we multiply all the edge weights on on all the edges crossing this loop by W, and we multiply each edge weights for each edges crossing this loop by Z inverse. And then and this is and then we define the magnetically altered Kastlin matrix, which is the adjacency matrix of this graph, which is with the rows indexed by the white vertices and the columns by the black vertices. So this is a construction going back to Kenyon, Okonkwo, and Sheffield almost 20 years now. And using that object, we define the characteristic polynomials, the spectral curve, and the amoeba in the following way. So the characteristic polynomial is simply the determinant of this magnetically altered Kastlin matrix. So this is a polynomial in the variable Z inverse and W. And it's a degree K polynomial in Z inverse, and it's a degree L polynomial in the variable W. And the zero set as a subset in C2 is the spectral curve. And this, is some curve, and to visualize this curve in C2 in a nicer way, you can consider the amoeba, which is the image in R2 of the log map, which takes Z, ZW to log of absolute value of Z, log of absolute value of W. Okay, so let us go to an example so you can see what these objects actually are. So let us start with a uniform case. So as K and L is equal to 1 and all the edge weights are 1. Okay, so what happens then? Well, if you do this construction and you get your characteristic polynomial, it has this form. So you see it's a degree 1 polynomial in Z inverse, and it's a degree 1 polynomial in W. The spectral curve is simply the subset in C2 fulfilling this relation between W and Z inverse. And the amoeba is the interior of this thing here. So it's a subset in R2, and it has this like tentacle types of asymptotes. So if you look when Z goes to 0, then if you look close, then log of Z here goes to minus infinity, right? So that's why you get this asymptote here. And as well, if Z goes to infinity, then well this goes to infinity. And similarly, if W goes to 0, then well log of W goes to minus infinity, and log W goes to infinity, and then you get this asymptote. Okay. And if you increase your periodicity, you still have the same kind of structure. It's a little bit more complicated, but you still have a similar structure of your amoeba. So now this is a case where K and L is equal to 2, and here K and L is equal to 3. And we still get the subset in R2 with a number of tentacles pointing actually in all directions here, right? But now we also get these like compact loops inside, so the holes in the amoeba. Okay. And okay, here, you can, you don't need to look at exact formulas, but you can, from the edge weights, you can really compute what is this asymptotes of the tentacles in a rather easy way. And generically, these amoebas has exactly L tentacles here and here. It has K tentacles here and here, and it has K minus 1 times L minus 1 compact ovals. That's true generically. In general, what can happen is that some of these tentacles merge together, as well as some of these loops can shrink to points. But that's the only thing that can happen. So for instance, like two of these loops cannot like merge together, and they cannot like go to the boundary or something like this. Okay? And why is this a very nice thing to look at? Well, it's because it was proven, again by in this paper by Kenyon, Okonkov, and Sheffield, that the spectral curve which you obtain from the diamond model is a so-called Hanna curve. And what does that mean? Well, it means that this map going from the amoeba to your spectral curve is a 2-to-1 map, which means that you can think about the spectral curve simply as your amoeba, or you take two copies of your amoeba, you glue them together along the boundary of the amoeba, and that gives you your spectral curve. That's how you can think of it.
Thomas, when you say at most 2-to-1, does it mean that there are some cases when it's 1-to-1 actually?
That's exactly when one of the, so for instance, if one of these compact ovals shrinks to points, then you get some kind of singular curve. So and at that point it will be 1-to-1, because it's, I mean, yeah, sorry, yes. So along the boundary it's 1-to-1, but in the interior it's 2-to-1, except when one of these ovals shrinks to a point, because then it's like, you know, the boundary goes to 1. But yes, exactly, along the boundary. Yes. Okay? So let me continue with the action function. Okay, so what is the action function? So now we have one object, which is the Aztec diamond, right? We have the amoeba here, which comes from the weights of the Aztec diamond, but it doesn't see the boundary of the Aztec diamond, right? We just took the weights and we embedded it in the torus, and that gave us the amoeba, right? So now we will connect the two objects. Okay, what we do is that for each point in the Aztec diamond here, psi eta, we define we define the action function. So for each point in the spectral curve, or think of it in terms of the amoeba, the action function is given by this form. It has some part which is rather easy and one part which is slightly more complicated. So, wait, sorry. So the action function is given, so k is given by this formula, so it's k over 2, 1 minus psi log w minus L divided by 2, 1 minus eta log z. So you see this w and z are the coordinates in the spectral curve, and psi eta are the points in the Aztec diamond. And then we have this additional term, log of some quotient of prime forms. And I will not go into and explain exactly what these prime forms are, but you can simply think about these as meromorphic functions, or at least locally meromorphic functions, such that it has a 0 exactly at the angles, and it has this set of angles. So this object here has zeros at these angles, and it has poles at these angles. Yeah, so sorry, yes. So that means the points at this set of points at infinity, and it's 0 at this point, set of point at infinity. Yes. Yeah, maybe I should have said that. Like, I mean, we compact this spectral curve by adding the points at infinity over here. Yes. So that's just a function at this point, right? And okay, I will not really explain to you why it appears, but so if you don't understand this slide, that's completely fine. But what we do is to consider the inverse of the Castling matrix, which is kind of which is the object which describes the local behavior of the dimer model. And we can express it as in terms of a double contour integral on the spectral curve. And it has this form e to the power of n, where n is the size of the Aztec diamond, times these action functions. And then we have a lot of other things which I will not go into here. But this is a form which is very suitable for steepest descent analysis.
So how do these formulas know about that you're dealing with Aztec?
That's really this part here. That's
You did not explain, okay.
yes, I mean yes, I mean this formula. I mean I can give another talk where I explain this formula, I think, but I think.
And G is not something that you're also explaining.
Yes.
Does G remember the Aztec?
Yes, that's a part of the Aztec. Yes, yes. So okay, so
It's irregular, it doesn't go to infinity.
so basically, what is this? Okay, so it's a double contour integral on the Riemann surface, and these action functions. Yeah, how should I explain this in a good way? So I'm not sure if I can do that in a quick way, but like the boundary condition really comes into here. That's really where the boundary conditions of the Aztec diamond. But that's not the entire story here. I mean, if you try to generalize this to other domains, I mean, there are too many questions to say that this is only the thing. Here, these are not really like meromorphic function on the spectral curve. And part of G is to compensate for this that they are not meromorphic on the spectral curve. There are more into G, but yeah.
G is not stand for group function or something?
I don't know really what.
Maybe I can ask the following.
Yes?
Suppose we take this function and apply k, and we should get 0. I mean, there's some combinatorial identity involving this stuff.
Yes, yes. And
Sum of 4 of them equals 0, or something like that.
exactly. So you can do that. You can hit this with k, and then it's like part of G, but it's also part of this one, right? Will make sure that it's the identity inside the Aztec diamond, and then on the boundary on the Aztec diamond, you need to use this part to see that it's that is the inverse. Yes.
So can you have a proof along these lines? Can you just check directly and then forget about all this advanced stuff? You
Yes.
kind of get this formula somehow?
Yes. I mean, for this case, yes. If you ask me if you can, do this for other, you can make a clever guess for another domain, I will not answer really if that's possible or not.
Oh, replace, powers by inhomogeneous products. It's one case. That might
Say,
help. Replace power z to the power w to the power by inhomogeneous products. That would be a good guess to try to see what boundary conditions you get from that.
maybe. Yeah, maybe.
So when you take isorigonal weights, which parts of this vanish exactly? Like this should simplify it very much, right?
These are kind of sophisticated questions.
Yeah.
Yeah, I mean when all the halls shrink.
I don't think I can answer that from the top of my head. Yeah. Okay, so I mean, and this is a rather like this is both technical and a rather. I mean, it's actually not it's a rather nice formula, but it takes a little bit of explanation to really do it properly, and also to explain how you get there. It's really like half of our paper is to really get this kind of formula. So it's yeah.
I think for isoradial weights, this ratio of prime forms that you have there just becomes a rational function. Okay.
Okay, so what I want to say with this slide is that like this is a perfect, this is a perfect formula for steepest descent analysis. Okay, if you know what steepest descent analysis is, then you understand why this is the case. If you don't, okay, don't worry about it. But the thing is that what you want to do is to look at critical point of this action function. That will kind of describe the limit. And that's also what we do here. So we have, this action function, and we look at critical points. And what you can prove is that it has a number of critical points, and you can kind of locate where these critical points are. So it will always have a critical point between each of these points at infinity. Not this type, which changes the group, but between the critical points in the same group. And then it will always have 2 critical points on each compact oval. Moreover, there are 2 more critical points. There are always 2 more critical points, and these will determine which region psi eta lies in. So more precisely, these 2 last critical points, so what happens is that if psi eta lies in, let's say, the frozen region here, up here, that means that this second pair of critical points lies on this boundary over here. So it's 2 critical points over here. If this point instead were, I think, here, that would mean that this oval, this boundary had 3 critical points. So the 2 extra critical points lies here. If you are in a smooth region, it means that the final 2 critical points lies in one of the compact ovals. So in total there are 4 here. And finally, if you are in the rough region or liquid region, it means that you have a critical point in the interior of the amoeba. And remember, in the interior amoeba, you have a 2-to-1 map, right? So it's 1 critical point here, and then you also have the other one on the other sheet of this amoeba. Yes?
In the smooth region case, how do we choose the compact hole it's attached to?
Say again?
You said that in the smooth case, it's attached to one of the compact holes.
Yes.
But how is it chosen?
So for each smooth region here, so in this case, maybe you can't really see it in this picture, but you actually have 4 smooth regions. And this is what we'll see in a bit, but you have 4 smooth regions. And depending on which smooth region you will be in, you will be in different compact ovals. Okay?
Could you show the previous slide again? So you have a map from the plane to the plane, right? And, I'm just trying to. I mean, on the next slide, you vary Q and Xi and Et, right?
So here, psi, you should think of psi eta as fixed. So maybe I take psi eta to be here. I forget about this one, I forget about this one. So it's only the yellow one. Then I will see all the red ones somewhere in that location. And in addition, I will see these 2 yellow ones.
These are the Q's as functions of Xi and eta, right?
Say again?
These are the Q's as a function of Xi and eta.
Yes.
Maybe it's a silly question, but I don't understand can you define what's the difference between the rough and the smooth? Like sort of on the surface of it.
On the surface, yeah, oh yeah, sorry, I think I forgot to tell you that, like, in the frozen here, completely fixed, right? Here, the correlation between dimers, so if you take two dimers and you see what is the correlation as the, the distance between the dimers increases, that decays exponentially over here. In the liquid region, it decays polynomially. I think it's by a square, or the distance squared, I think. So yeah, so that's the difference.
If you apply this urban renewal dynamics to these weights, do the points, these critical points, do they move around?
The critical points moves around. I would say no. I'm not complete. So in the urban renewal, this would not change these guys, because these are, I mean, under the urban renewal, the spectral curve stays the same, right?
The spectral curve stays the same?
Yes.
But the individual edge weights, they change.
The parameters change, yeah. So
Yeah, but in this guy, there is nothing with edge weights, right? And that's completely determining your critical points. So because these guys are, the angles or the points at infinity in your spectral curve, and that will not change.
You seem to know the total number of critical points of this function. Is it because E are some kind of polynomials, or how else do you know that? O but 2 you say, so you seem to know the total count, right?
You know the count. And it's simply because, I mean, it's actually kind of a nice, you look at the differential of this guy and you can say exactly, where it has its pole, how many poles you have on a compact Riemann surface. And if you know the number of poles, you know the number of zeros, and that kind of gives you it's just a counting argument in that way along those lines. Okay?
So just to clarify, this has nothing to do with divisors or usual points of the ovals, or does it have to do with?
It does, but I'm not telling that story part here really. And I can explain a little bit, but maybe it will take too much time if I start to tell you that story. Any other questions? Or okay, so one thing with this definition is that we get the map from the liquid region to the interior of the amoeba very naturally, right? You take a point in the liquid region, the unique critical point in the interior of the amoeba is how you define your map omega. Okay, I think I'm finally ready to tell you all what our results actually are. Maybe first I should mention what our assumptions in this thing is for our results. So what we do assume is, we assume that these tentacles lies to the left of the y-axis, and these guys lies to the right of the y-axis. It's a technical assumption which I think it's not too difficult to remove, but we kept it like that. We also assume that, some genericity assumption that all the compact ovals are present and we have K tentacles here and L tentacles here and here. And this is true generic, and it's, yeah. Okay, so what did we prove? So the first result is that this map I defined, taking, from a point, okay, maybe I've changed my parameter from UV for this to really be true, but you take a point in the liquid region, you map it to the amoeba. This map is a homeomorphism between the liquid region and the amoeba. Moreover, if you take this map, take it to the boundary, then this map preserves the slope of the boundary. So if you go here, let's say the Arctic curve has this slope, that means that the image in the amoeba is the point on this part with the same slope. Moreover, this map reversed orientation. So if we follow the Arctic curve like this, it means that we are following the amoeba like this, in this direction. Okay?
Could you flip amoeba like?
Say again?
Could you flip amoeba so that it maps better?
Actually, I think this is it's the better way of do it, and maybe that's because this has a few implications which is kind of nice. But probably you can map it around, and I don't know. Maybe it's a better way, but I like this way. Let me put it like that.
That was a choice in 2006, probably, right?
Say again?
This was a choice in 2006. To reverse it.
I think so. I think it's naturally orientation reverse.
I think so too. Yes. I think so. And one thing, this is a homeomorphism. So one thing is that you have a one-to-one map between the smooth regions and the compact ovals. You also have a one-to-one map from the frozen regions to these unbounded complements of the amoeba. So you have like this corresponds to this one corresponds to this one to this one. It also implies that the liquid region or rough region is locally convex. And the reason is exactly this reversing thing, that it preserves your, the tangent line, but it reverses orientation. And it's known that the complement of the amoeba is convex, which then gives us that the liquid region is convex. It also tells us how many cusps you have in each of these regions. And the reason is kind of, so if you take this one and you go around 1 times in this direction, we are going around 1 times in the opposite direction. But the tangent line is always the same at all smooth regions, and if you do this, and this needs to, add up in some way, and for that to happen, you need exactly four cusps. And it also implies that you have 1 cusp here and 1 cusp here. Okay. Maybe, I have, how long do I have? Okay, yes, perfect. Then I can tell you. Okay, any questions on these results?
Why does that give you exactly 4 cusps? Doesn't that give like at least 4 cusps?
No, because it's, you need to go exactly these ones should go, like the angle should change exactly by -2 pi. And the angles here should change exactly by 2 pi. Any other questions? We are also looking at the height functions. Okay, so what is the height function? Maybe, okay, you can define it like maybe the easiest way to explain it is that you take some reference dimers. So here I consider all the north dimers, which are the ones in red. If you take any dimer configuration and add them on top of each other, you get these like non-intersecting path showing up here. And the height function is defined for our purposes as the function having these non-intersecting paths as their level lines. Okay. So it's 1 here, and then you cross one of these paths and you get 2, and then you cross another path and you get 3. Okay. And if you plot the height function against the Aztec diamond, you get something looking like this. And there are some, maybe I will not show you, but there are some, maybe I will show you because they are very nice. I think we can. So you can see it, just to see the action function. So here is a random sampling of the Aztec diamond, right? And then this would be the height function. And I always try to rotate this so you can see, but like you can, for instance, kind of see that the smooth regions here are completely flat, and then the rough region is like it's maybe or is like curved, and then you have the frozen regions which are also completely flat. And we get an explicit expression of the height function in the limit. So if you take this height function, you take the size of the Aztec diamond to infinity, we get a limit which is an explicit expressions in terms of this action function. So the limit here is the integral over the action function, or the differential of the action function, where this curve, it goes from the critical point in your amoeba. So let's say we are in the liquid region, or then maybe your critical point lies here. You take any curve going from the critical point to any point on this component here. And that gives you a curve in the spectral curve. So maybe, you know, if you take the double cover, you get the curve looking like something like this. And that's the curve for the liquid region. In the gas region, you have your critical points on the compact oval. You choose one of them, or you choose a point on that compact oval, and pick a curve going from that compact oval to this boundary, and that gives you the curve you are integrating over. And the slopes are expressed in this. In the slope of this height function has this form then. And so that means more explicitly that you can parameterize your surface, right? Going with by the amoeba, by the interior of the amoeba. You can parameterize the liquid region by your amoeba, because you can actually get an explicit, maybe a bit complicated, but still explicit expression of the inverse of this map. So you take a point on your amoeba, that gives you a point in the Aztec diamond, and as your third coordinates, you have the limit shape. So that gives you parametrization. Okay, and maybe as a last slide, I should say that we also prove, I will not go into that in too much detail, but we also prove local fluctuations. So it means that if you take a point in your Aztec diamond, you zoom in at that point, you get like some probability measure on the square grid. And we prove that what you see when you zoom in like that is precisely the ergodic translation-invariant Gibbs measures. And another way to explain this is that we simply compute the large N limit of the inverse Castelli matrix and show that it has this form in the limit. Okay, so just a short recap. I think now you recognize these objects, right? So you have seen how these two pictures, the Aztec diamond is connected with the amoeba, and also how you can parameterize this limit shape in terms of the amoeba. Okay, thank you for